Good. So, about architectural motifs. An important one that we have seen in the unit already are the skip links, and they are at the heart of ResNets. And you see here one of these ResNet modules where basically whatever comes from the earlier layer is sent into this convolution layer, but it's also added to the output of those two convolutional layers. And if you now look at the backpropagation, you have this motif that the gradient on the one hand gets sent through the convolution layers, but on the other hand it gets sent around those. And this allows gradient to reach the early layers of deep networks more easily. And this pretty simple idea of using these skip links made for a jump in the depth of networks that people started training. Yeah, so they went to 30 or 50 or 100 layers, which could not previously be trained effectively. And what this type of image does not show here is the actual spatial resolution, because I'm sorry, the resolution here, the beamer is not so quite focused. All right, here. Because we have a couple of pooling operations or of here transpose convolutions. So that means the original resolution, it is halved here, and it is halved again, and it is halved here, and there, and there. And this is for the classification case, so similar to VGG, you go from full resolution to just a vector, of a one-hot vector indicating what class you have. But the same kind of architecture, ResNet architectures with less downsampling, are also used for semantic segmentation tasks. An extreme case of these skip links was the dense net, where in each of these dense blocks you had skip links from one layer to all of the following ones. Okay, and this you've also seen in the units. So skip links is something that's universally used today. All right, then here the first layer we already looked at, but what do filters in later layers learn? And this was revealed a little bit by these kind of they were called deep dream images at the time, and they were created as follows. You would input some image or photograph, and this could even be just a pure noise image. And then you would, in a later layer, look at the activations of a particular neuron, and you could then change, so do backpropagation from this particular neuron, and this time not to the parameters, but to the input image. So you could do backpropagation of not the parameters, but of the input image with respect to activation of a particular neuron. And if you picked an amphibic neuron, or what you can then in hindsight interpret as an amphibic neuron, you would, for example, obtain this kind of image. And if you hit the neuron which codes for convertibles, then you see convertibles everywhere. And if you hit the neuron that codes for dog faces, then suddenly dog faces start appearing everywhere. Yeah? And before stable diffusion and so on became available, this was the first time that neural networks were used to create visual art in this somewhat crude fashion. You could start with a noise image, or you could start with some real image, and then you could tweak the real image so as to fire up or increase the activations in one particular neuron, and then it would give you, those funny versions. So if you want to look at more of these, deep dream is what they were called. All right, and here I have a question for you, because this relates to adversarial attacks. So an adversarial attack means, how do you change an image, or how do you trick a neural network into seeing something that's not there? There are various ways of adversarial attacks. One which is a bit famous is to, print a stop sign on the back of your T-shirt when you're a cyclist, and let the car see, oh, there's a stop sign, I should stop. But there are also more subtle adversarial attacks, in particular where you can tweak just a few pixels in an image to let the classifier believe that there is a panda in the image when there is not. Yeah. So please take a moment to discuss with your neighbors how to create adversarial attacks, and those who already know, they can think about how to defend against adversarial attacks. Yeah. Please take a moment and make suggestions afterwards. Shown here is a typical example of an adversarial attack. You take some image, you add a little bit of something to obtain a new image, which for the human eye is indiscernible from the original one. Now, you know, I've not made these images. I don't know whether this is fake or not, but in real life, when you don't defend against adversarial attacks, then really, you know, these eyes by human eye, or the new image by human eye is not discernible from the original image. But if you feed it into the neural network, which does not defend against adversarial attacks, this would now recommend a yield instead of a stop sign. Okay, so can you please repeat or explain, you know, how would such an adversarial attack be conducted? Yeah.
So I know a couple of artists online that they suggest like using something that's called glaze, and I suppose I don't know the details, but how I suppose it works, since we can like if we know the structure of a network, we can kind of trace what it does with the pixels and adjust them just a bit, but enough so the representation, like the I guess the encoded representation would be different. But I always suppose that it's not a good enough protection, because if you could, like for this, if you could change your network even a bit, then you would need another way to protect the image.
Yeah, so like you point out, these adversarial attacks, a big difference is whether or not the attacker has knowledge of what architecture is being used. Yeah. Good. Can you say it in words? It's too far for me to walk. Yes. So we have our neural network always is a function of the input and the parameters. And what we can, and this function, if it's a classification neural network, if we output 1,000 different classes, this here is a vector with 1,000 entries. Yeah? So normally we wrote p times 1, where in our case here, p for 1,000 classes would be 1,000. And now what we can do is we can look at the partial derivative of a particular class. So let's say we look at that component of the output which corresponds to the yield sign. And now we evaluate the derivative with respect to, this time, the input. Yeah, so this will tell us how do we need to change the input image so that the probability of yield goes up. Yeah? And we just use standard backprop, but we don't backprop. So this time we don't minimize a loss, and we don't backprop with respect to the parameters, but we backprop the activation of one particular class with respect to the input. And then the result, so what I've written here, the result can look like so. And then if we add a little bit of that to the input, then we can provoke the network into making the wrong predictions. Okay, so this is what, if we have access to the internal workings, what an adversarial attack can look like. And now, of course, in this battle of wits, how do we defend against adversarial attacks? Yes? Yes. So you were suggesting to, use this adversarial attack, for example, this attack, and then use the resulting image and add that to the training data, of course, with the correct sign. Yeah. So here we would add this to the training data and say, this is also a stop sign. Yes. Other suggestions? Yeah, but this is fine. This is basically it. Yeah. And this is a little bit like this battle in generative adversarial networks, where you try to fool the network, and then you try to harden the network against that kind of fooling. And yes, these attacks they are a concern for people developing networks to put them into driving cars and so on. Okay, but here the headline was, what do neurons learn? And in essence, in the first layers, neurons learn edge detectors and blob detectors. And what they learn in later layers are representations of higher order concepts. So, for example, if you train a neural network on all kinds of images, you find neurons that react strongly to wheels or to circles. And then you find neurons that react strongly to faces and that react strongly to airplanes and such. So, and this is, in particular, the thing with the wheels is interesting because the neural network might have been trained with the concept of, cars exist and bicycles exist and pedestrians exist, but it has never learned explicitly about wheels. But the neural network has somehow, in the process of training, figured out that wheels or understanding about wheels is a useful building block for higher order concepts. So neural networks somehow, by training through many, many iterations, are able to extract these meaningful building blocks. All right, then I wanted to talk a little bit about explainability. And the example here I have is again from medical domain, or this is also very much a concern in digital pathology applications. So, but the same holds in astrophysics. So if you have a classifier that says, something is a supernova or not, it's very nice to have your classifier successful on the training data, and hopefully it's going to do well on the test data, but you would really like to understand, what in the image does it look at? And here is an example of what in the image does it look at. And here, by the way, the actual glioma, if I understand correctly, is here, but the neural network says it's a glioma because of there. And then you can speculate about, all right, the glioma, it pushes the brain into regions where it shouldn't be. Yeah? So there's this, it's squeezed against the skull here. So maybe this is actually informative. But sometimes neural networks do also learn nonsensical things. Yeah? And in the original paper, I think that proposed GradCAM, there are also examples of when your training data is not properly curated, it can be that the network learns, to read the label in the image, like whatever, all the tumors were acquired on a Philips scanner and the controls on a GE scanner, and then it learns to read Philips versus GE and not look at the actual disease. Yeah? So these are useful techniques to try and understand what has the classifier picked up and is it anything reasonable at all. And to explain how it works, I here have a figure not from the original paper, but from, you know, one of the zillion COVID-19 papers, which, however, does a better job of explaining than the original paper what it does. And it works as follows. So we have some input image. We train, you know by now what a ResNet is. Yeah, this residual network with the skip links, 50 layers deep. And this type of ResNet was not, this has, the network has, even if it runs classification, you can look at the final layer which still does convolutions. Yeah, so this still has spatial resolution, this layer. And then come the pooling and the fully connected layer. So this is the MLP part, and then you classify in does this, you know, does the CT scan, the chest CT, belong to somebody who does or does not suffer from symptoms? And now you can look at the activation images. So you can ask in a particular image, how would I need to change my activations in the final convolution layer so as to make this image look more or less like showing COVID symptoms. And so these are still images, and these images are then simply summed up. Yeah? So we just get for each of these convolutional maps here a single number that sums up their average activity, W1, W2, W3. And these numbers are then multiplied with the actual activation maps. The result is added up, it's sent to a rectifying linear unit, and it gives this type of picture, which is called GradCAM or gradient camera, and highlights where did the classifier look in deciding that an image was of this or of that type. Okay, and that's one useful approach to try and understand what a deep convolutional neural network does. Yes? Yeah, so this is, there is no decoder here. It's not an autoencoder. It is, this type of structure is meant to say we go from the original resolution of the image to increasingly lower resolutions with increasingly more channels. Let's look again at the original ResNet paper. We have, unfortunately, they don't give here explicitly the spatial resolution, but let's say we start with an image which is 512 by 512. Yeah? Then here it is only 256 by 256, then it's 128 by 128. And at this stage, it's only 64 by 64. And this other number here, that indicates the number of channels. Yeah, so here we had 64 channels, here we have 128 channels, then we even have 256 channels. So we go to lower and lower spatial resolution, and there was talk about a last convolutional layer. So that's the last layer which still has which still has a decent amount of spatial resolution. And this is why it is sketched here by this trapezoid. And yes, you can call that an encoder. Yeah, it goes from high dimensional input to some lower dimensional representation. And one could add a decoder to have a side loss, an auto-encoding side loss to help train this thing. And that would be a useful approach if you don't have enough training labels. If you do have enough training labels, then you can simply train this here in a supervised fashion. Thank you. Any other question? Comment? Yes? Okay. What is W1 to W3? So these here are activation maps, or they can be also this type of quantity, which is also has the dimensions of an image. And then these activations or these derivatives are simply added up. So that's missing here. This thing just added up gives W1, and that thing added up gives W2. So we turn an image into a scalar. And then these scalars are multiplied pixel-wise with the activation maps, and the result is added up. And miraculously, we overall, get something that seems to be informative. This is not, how should I say, this GradCAM procedure is not something you can derive from first principles. It's not the only way to do it. It's not the right way to do it. It's a way which has become quite popular. Yeah? And there are many derivatives of this. There's GradCAM++ and other versions. And people find this useful in understanding what a big CNN with millions of parameters does. All right. Then loss surfaces. There was a time in 2018 when in parallel a couple of papers came out that were looking at the loss surfaces of modern architectures, and shown on top here is an example of an architecture with or without skip connections. And this is now in the space of architectures. So what we see in the third dimension is the loss, lower is better. And if the network has 1 million parameters, then this loss is a function for a given training set. Then this loss is a function which lives in a 1 million dimensional space. Now we have difficulty visualizing what's going on in a 1 million dimensional space. So what these authors did here is they choose 2 random directions around the minimum. And then they do the scaling of these 2 random directions in a bit of a smart way. But still, these are just random directions. Still, if you repeat this experiment, you see that the loss surface tends to be more rugged if you don't have the skip connections. And so this was used as an explanation, as a hand-waving explanation of why skip connections do help in the training. It's a bit hand-waving because the scaling of these axes and so on is, that's a bit questionable. Then there's work we did, so Felix Draxler, who recently defended his PhD, and now the PhD he did with Ulrich Köth, and now he moved on to California for a postdoc. At the time of his master's thesis, we were looking at again in this 1 million dimensional space of neural network architectures. So here only 2 dimensions are shown, but if the network has 1 million parameters, then really we have 1 million dimensions, and we have the loss surface here color-coded or shown in false colors as a function of where we are in this 1 million dimensional space. And so any point in this space is a specific neural network. So we can do gradient descent or stochastic gradient descent once. So we can train our neural network with some seed, some random seed, and we end up here. And we can train our neural network with a different random seed, and we end up there. And if we now interpolate in parameter space linearly and look at the loss, then the neural networks are terrible. But if you try harder, you can actually find low loss connections that are highly nonlinear between these different neural networks. So this is a neural network. All of those are neural networks, and they are different in the sense that they make different errors, but they all have equally low loss. And this is what I meant when I said, in textbook pictures about what's going on in gradient descent, in stochastic gradient descent, and so on, the loss surface is always depicted as something like so. And if we're lucky, it's shown to be, not just ellipsoids, but a bit more complex. But it still suggests that the optimum is just a point. And this is definitely not true, because for example, in multi-layer perceptrons, I can make the outputs of one layer a little bit smaller, and then I can make the weights of the next layer a little bit larger, and the two things will cancel each other. The neural networks will have different parameters, but they will be operationally completely identical. And so if one of them has a low loss, then the other of them must have an equally low loss. And that means that the minima are not really points, but they are manifolds. So now this is difficult to imagine in a million-dimensional space, but I have here, just some random 3D pictures to illustrate how I think about what a minimum of a neural network looks like in parameter space. So, okay, this here is on the left is some cosmic web, and on the right-hand side is a micro CT image of a foam. But what I mainly want to show is that the minima are not distinct entities here, but the minima are somehow, or the minimum, these are somehow connected entities. And these are, low-dimensional attempts at explaining how I think about it. And by the way, this was with Manfred Salmhofer and Kambis Veshkini. You might know Manfred Salmhofer from mathematical physics lectures, and this was a very fun joint project on something completely different. We here have a hand-waving explanation of how can this happen, such a low loss path. Here is a tiny problem, the XOR problem. So orange is one class and blue is a different class. And we have seen how to construct a multi-layer perceptron to perfectly solve this problem. And in the first layer of this MLP, we might have two perceptrons, which we have here called Alice and Bob, and we have the normal vectors showing which direction they point. And if we now try and exchange Alice with Bob, so we have this neural network, which is perfect. We have that neural network, or MLP, which is also perfect. But how do we transition from one into the other? If we transition like so, in between we will have an imperfect of neural network. We will have a loss which is non-zero. But if we make our neural network wider, so if I add a third perceptron to the first layer, Charlie, then Charlie can take the place of Bob. Bob can do whatever it wants, and it can have its output switched off, and when Bob has reached the position of Alice, Alice can walk around and do whatever she wants, and then in the end, Charlie can leave again. And in this way, we have constructed a path of zero loss. And indeed, we observe these low loss connectivities only in networks which are sufficiently wide. So the neural network needs some minimum expressivity to really feature these low loss paths. All right, and this is the third paper which came around roughly at the same time. Andrew Gordon Wilson and colleagues they were looking at the following setup. They had a learning rate. So how big is the step size in our stochastic gradient descent, which they lowered over time. And here you can see in the test error plot that this gives a good neural network. And then the learning rate was increased again. So in a kind of annealing process, yeah, like you inject more energy, the network became worse. And then it was again lowered. This is another good network. And this is another good network. And that's another good network. And here you can see the distance from the starting point. And so all of these are good networks, but they're not identical. Yeah? They are different. And this was a particular procedure to find different good networks, which could then be used also for ensembling. Okay. And the last idea or set of ideas I want to share for today are ideas that are useful when you do not have enough training data. And this has been one of the most lively fields in recent years. There is supervised and unsupervised approaches. In the supervised approaches, what has been really successful are multimodal networks, where we can take, for example, a set of input images, and we can take a set of texts that we think pertain to the images. And then the image, or each image, is embedded into some space. The text is embedded into the same space. You know, that was, when it came about, that was a pretty drastic idea. For this, we definitely need transformers. This could be done without transformers, but in practice also transformers are being used here. And then each image becomes a point in a, for example, 4096 dimensional vector space. Each piece of text becomes a point in the same vector space. And in this, the learning task then is to say that the matching images and texts should have a high similarity. I can measure this, for example, by just the dot product. Matching images and text should get a high similarity. And images with the wrong texts or with other texts should get a low similarity. So we can apply that kind of loss. We want high values along the diagonal. We want low values on the off diagonal. We can apply this kind of loss and then do back propagation into both our encoders. And this you can do with general images, or you can do it with data from specific domains. So in this case, here's an example from digital pathology: plenty of images, plenty of texts, one text that goes with every image, and then the very same kind of machinery is used. And if you do this on 100 million images, then you get very good foundation models for digital pathology. But for this, you need at least weak labels. You need at least some confidence that the first text actually matches the first image and the second text matches the second image. The data doesn't need to be perfect. In particular, if you have lots and lots, you can just take web pages, and you take the image as the image, and you take the text close to the image as the text, and then you will hope that on average this does the right thing. But of course, the better the quality of your labels, the easier the training. But for this, you need at least weak labels. And then there are approaches where you can learn something useful without labels. Or where you can easily generate millions of labels yourselves. So for example, I can take any image, any real image, and I can add noise to it. And then I still remember what did the original image look like. And then I can train a denoiser to, given the noisy image, give me the real image. And that, by the way, is an important step in all of these diffusion, stable diffusion methods and so on. Or we can use autoencoders. or I can take a color image and turn it into a black and white image and still remember the original color image. And then I can task the machine with, well, predict the colors. And then incidentally, once the machine has been trained, I can use it on really old photographs to colorize them. And you can argue that, well, if the image has learned how to correctly colorize any image, then it implicitly has learned something about people and about trees and about houses and so on. Yeah, it has implicitly learned something about the image statistics. I can also take an image and I can occlude a part of the image. And then I can ask the machine to predict what I just occluded. Or I can cut an image into pieces and mix them, and then ask the network to puzzle the image together again correctly. And again, if it manages, I can say that, all right, this network has really understood something about the way our world or the way that galaxies and so on, whatever is your object of study, the way these objects are structured. Or in temporal data, you can use cycle consistency. So if you have a video, you can start anywhere in the this computer is still here, but maybe it thinks that it's time to conclude the lecture. All right. I will not be able to show the images explaining cycle consistency, and we will look at contrastive learning then in the exercise. All right. Thank you very much. Talk about graph neural networks next time.